I want to talk a little bit today about some of the aspects of my research in this area. So my own research started in the area of computer graphics, which is basically, all the technology that is required to manipulate and generate images with computers. And virtual reality is, in that sense, one aspect of the broader field of computer graphics. So virtual reality really comes with the promise that you can plop on these VR goggles and dive into a virtual environment that will create this sense of presence in this virtual environment, where basically you will see your virtual scenery as you would see visual information in the real world. That's really the promise that virtual reality technology has brought to the table, and that is, with what is currently possible, that is becoming a reality, that we can really do this. But this is a very, very difficult technical challenge to build systems that can do this. The image synthesis that is involved here requires multiple steps. It starts, with sensing the head motion of a user that's wearing a display, and then taking that head motion and the current position to generate a virtual image from the viewpoint where the user currently is, and then send it to the display. So this is really challenging because it has to happen very, very quickly. There's this notion of the motion to photon latency, which is basically the time between the user's head motion and the time when the corresponding image is displayed on the VR headset. So this motion to photon latency needs to be very low. It needs to be below about 20 milliseconds for VR applications. And otherwise, users will experience motion sickness, because basically the visual information that they see doesn't correspond, accurately enough to their movement in the physical space. So that leaves very, very little time for the computer system and the algorithms that actually produce the images to send an update to the VR display. But this is very challenging because we have millions of pixels per image that basically need to be computed. And what you would really like to do to achieve presence is to provide photorealistic light transport simulation. So the images ideally that we would show would look like photographs. So we're not always displaying real environments, of course. So I just have this example from a well-known movie that clearly is not real, but the visual quality of the image is like a photograph. And this is because to produce this image, a light transport simulation has been performed that, that basically simulates how light would bounce around in a virtual scene like the one you see here, and then form an image in a virtual camera. So to do this, you have to do this light transport simulation for millions of pixels in less than 20 milliseconds, and that's very challenging. So fundamentally, the light transport simulation is quite simple. All you have to do is essentially simulate all the light paths that can carry light energy from a light source in your virtual scene to the pixel of your VR, to a pixel in your VR goggles. So this yellow path illustrates such a light path. But each pixel will, consist of basically contributions of light from all possible paths that light can take in your virtual scene. So there will be many, many of these light paths, and to get a high quality image, you will have to simulate them and do this for millions of pixels at, in less than 20 milliseconds. So that's very, very challenging because it's a lot of computation. Now, with current VR technology, we can't really do this just yet. So this type of photorealistic light transport simulation is really a research topic and sort of a holy grail that still needs to be achieved. So in my work, the goal is to make steps, towards this holy grail of really having photorealistic light transport simulation in these virtual reality applications. And I just want to show you a few examples of my research and some ideas that we have developed to come closer to this ultimate vision. So the first one is what is called foveated rendering, and that's the idea that we will exploit the properties of the human visual system, where we really have a lower visual acuity in peripheral areas. So in a virtual reality display, you usually have to render a field of view of at least 100 or 110 degrees, so that the user is fully immersed in the virtual environment. But in the periphery of the display, that is far away from the point that the user focuses on, in that periphery, the human visual system doesn't see the image completely sharp. And you basically only get a blurry perception in these areas. So this tells us that we can focus our effort to render these virtual images to the foveal region in the center of the visual field, and we could produce images with lower quality in these peripheral areas. So that's the idea of foveated rendering, and that's not a new idea that we invented, but we invented a particularly effective way to do this, which is called kernel foveated rendering. And that's a collaboration also with Amitabh Varshney, the dean of our college, who also spoke in the introduction of this event, and some of his PhD students also. So with our approach, we basically save computation by reducing the image resolution in the peripheral areas. So you see this in these images here that get slightly blurry as you go towards the periphery. And in a virtual reality headset, you won't really notice this because this is in your periphery, and your visual system can't really see the difference between sharp or blurry images in those regions. So with this technique, we can achieve the same perceptual quality, but at 2 to 3 times the rendering speed. So we need 2 to 3 times less computation time to achieve the same quality. Another way that you could make light transport simulation faster is by simply simulating fewer of those light paths that I showed you before. But the problem with this is that this will produce grainy images. So it's almost a little bit like you take a photograph when there is not enough light and your camera produces, this grainy noise. That's a very similar effect here. But here this really comes because of the simulation, where we just chose to only compute very few light paths in each pixel. So that clearly allows us to accelerate the computation, but we end up with, not very pretty pictures. So one direction that we have been taking in our research is to leverage artificial intelligence-based techniques to improve that type of light path simulation. So here are some results from a research project that we concluded last year, or 2 years ago now, where we basically learn using AI-based techniques which of those light paths we really need to simulate and which ones we can omit. So in the visualization, you see this uniform random approach. That's kind of the naive approach, where you just randomly try many light paths, versus our approach to the right, where we use AI to figure out which of those light paths are really important, and we evaluate and simulate only those. And again, this comparison is at equal rendering time here. So you see that, at the same computational time that is invested, we get a much clearer image with less noise. So the key idea here is that we can use artificial intelligence-based techniques to figure out which light paths we really need to simulate. And here's a third example, which is AI-based denoising. So the idea here is that we could simply take a grainy image and then try to post-process it with some kind of image filter to get rid of the graininess. And again, you can do this very effectively with artificial intelligence-based techniques that essentially learn how to transform a grainy image into a clear image. And we have developed such a technique that takes a very little computation time, only a few milliseconds to do that, post-processing of the image that removes the noise. And in these images, you see the grainy input. This is called 1 SPP, because we only take one light path per pixel in our simulation, and that leads to a lot of graininess. And then we run our post-processing technique that essentially clears up the image with very, very little additional computation time. All right, so I just wanted to show you these a few examples. And as conclusions, I want to say that these innovative algorithms that we are developing, they will open avenues for novel types of AR and VR applications that are not possible with today's technology. And I think IMDM will provide unique opportunities for students to develop both such new technologies and at the same time also come up with new creative applications that will, be truly innovative in both a technical aspect, but also in terms of creative and artistic expression. So I'm very excited for IMDM to take off and make this possible.